Thank you. Good afternoon. I will talk a little bit about potential future application of gravitational lensing of gravitational waves as a tool for cosmology. And this is a work that I'm going to try to cover a body of work done in collaboration with several people, and many of them are in this audience, including Ankur and several of colleagues from the Lagovergo Kagra Collaborations Lensing Group. So let me start with just broadly setting the picture, and it's sort of become clear to us over the last few days that in the case of lensing of gravitational waves, there are broadly two regimes. One, the usual geometric optics applies, and that's, roughly speaking, this is valid in the case of very, very large lenses, in the galaxy or cluster scale lenses, where the corresponding gravitational scale is very large as compared to the wavelength of gravitational waves. You can treat the wave propagation as a geometric optics. And even in this situation itself, there are, you can see both the weak lensing, where you only see a slightly magnified image. And unlike in the case of lensing by galaxies, etc., we don't see any distortion because our sources are point sources, compact sources. So essentially, the manifestation of weak lensing of gravitational waves is some small magnification, which is very hard to measure. What is easier to measure is the strong lensing, where in the appropriate conditions, you can see multiple images. And because these sources are transients, they would appear at detected multiple times with a time delay. That is characteristic of the the mass scale of the lens. The second regime, which is very hard to observe in the electromagnetic waves, is the wave optics regime, where you have the typical scales are comparable with the wavelength of gravitational waves. And you can see very interesting diffractive phenomena, which will deform the observed gravitational waveform. So basically, the cartoon here, so in the case of the geometric optics lensing, you see a magnification almost always. You might get multiple images which look the same, except for a relative change in the magnification, a time delay, and a phase difference also. But here in the case of the wave optics regime, we saw similar pictures in the past few days. We see characteristic deformation in the observed signal because there are multiple wavefronts coming and interfering. And here is, for example, the gray line is the unlensed, usual chirping binary black hole merger signal, while, for example, the gray line or the red line shows how this would be the resulting lensed waveform, which is sort of micro-lensed by these small compact object of 100 solar mass or 1,000 solar mass. And at least in the case of simple enough lens models, one can compute these magnification functions. We have several interesting talks on that, and compute the lensed gravitational waves. We could also look for these waveforms, these sort of the lensing effects in the data. And in the case of the strong lensing, which produces multiple images, we're basically asking if you take a pair of events, two gravitational wave signals, which are recorded in the data D1 and D2, there are two possibilities. One is that these two pairs of events are produced by the strong lensing of a single merger happening somewhere, or they could be produced by two independent mergers happening at different parts of the universe. So you have two hypotheses. One is the lensed hypothesis and the unlensed hypothesis. So you can compute a Bayesian likelihood ratio between the two hypotheses given the data D1 and D2. And then one can compute it with various methods, and there are approximations used, and I'll a little bit about that. In the case of this single wave optics lensing, or sometimes called microlensing, you only have a single deformed signal. So you have only a data D. But again, still have two hypotheses. One is that this is microlensed by some point mass lens or some compact lens, or it is unlensed also. And the microlensing hypothesis, to compute the evidence, you have to introduce additional parameters that describe the properties of the lens, as well as the relative location of the source on the lens plane. And you can marginalize over those likelihoods and compute an evidence ratio or likelihood ratio to get a Bayes factor or a likelihood ratio between the two hypotheses, that one is lensed or unlensed, using a single observed signal. And we have had several searches to look for these lensing effects in the past 3 observing runs of LIGO and Virgo. And this is sort of one plot that kind of summarizes the results. This, for example, it shows the base factor, the likelihood ratio between the lens and unlensed hypothesis in the y-axis, sorry, the x-axis. And the larger values means smaller evidence towards lensing. The ratio is very small. And while this color shows the, this is a pair of events. So each of the dot corresponds to a pair of events. And the color shows the probability that these pair is associated with an astrophysical event, so-called P astro, if you're familiar with what the LIGO collaboration releases. In summary, we don't see any events that at least have a likelihood ratio close to 1. We don't see any significant evidence of any of them being lensed. On the right-hand side, on the other hand, shows the base factor or the likelihood ratio between the microlens hypothesis and the unlensed hypothesis obtained from the foreground events, from the third observing run, O3, the blue histogram. So you see some values with a log base factor of order 1, but now you have to ask how significant that base factor of E is. And if you do a simulation of unlensed events and compute these likelihood ratio between the lens hypothesis and unlensed hypothesis, you get a distribution because you're computing it from the noisy data. So there is always some probability that you get a base factor greater than 1. And that is shown by this orange. So in summary, the foreground, which is that we compute, is consistent with the background. So we don't see any significant evidence of lensing in the case of microlensing also. So in summary, we do not see any evidence of strong lensing or microlensing in the data so far. But even this non-observation of the lensing effects can be used to say something about cosmology. It's not very interesting yet. One is about the existence of primordial black holes, the possibility of them contributing to a good fraction of dark matter. And this, for example, the argument is following. If you do not see any, it's a microlensed event, if the significant fraction of the dark matter is in the form of primordial black holes in the mass range of about 100 solar mass to about 10 to the 5 solar mass, at least a fraction of these cosmological gravitational waves should have been lensed. The fact that we do not see any lensed gravitational waves put an upper limit on the fraction of dark matter in the form of primordial black holes in the mass range to 100 solar mass to about 10 to the 5 solar mass. So it depends on various model assumptions because we don't really know the distribution of binary black holes at cosmological scale, so one has to fold in some models. Depending on that, you get some range of constraints, and also depending on the prior that you get a slightly different constraint. But the most conservative one shows that not more than 80% of the dark matter could be in the form of primordial black holes in the range of 100 solar mass to 10 to the 5 solar mass. It's not a very interesting constraint yet, but I'll show you a little bit how these could improve in the future. Similarly, if you now think about the possibility of supermassive black holes contributing to dark matter, which is very unlikely because already is constrained by CMB, spectral distortion, etc. But if you think of this as a different way of constraining the same thing, if the dark matter is comprised of supermassive black holes, they would produce strong lensing of the LIGO-Virgo gravitational waves. So they would produce multiple images or multiple copies with small time delays of thousands of seconds or even smaller, because that is the scale of the mass that you're talking about. And the non-observation of such multiple events with small time delays can be used to put a constraint on the abundance of such supermassive black holes. Also, the work by Ankur, who is sitting here. And again, you get some modest constraints. These are not too exciting now because this parameter space is already ruled out by other observations. But this shows how, in the future, a non-detection of such lensed events could improve these constraints in the very near future with 1,000 events or so, which is expected in the next few years already. It's an interesting way of constraining this possibility using gravitational wave lensing. And there are some caveats. If you're interested, I could discuss that later. Now a bit more futuristic thought. As you know, there are several very active proposals and plans, actually much more than proposals, to build the next generation of gravitational detectors, primarily in the US and in Europe, called the Cosmic Explorer in the US and Einstein Telescope in Europe. And these can detect binary black holes out to very large redshifts. Practically, they'll be able to observe practically all the binary black hole mergers happening to the universe, probing redshift of 1 to 100, depending on the mass of the primordial of these black hole binaries. So, and the expected event rates are very large, reaching millions. So, even if the optical depth is less than 1%, you would expect a large number of these events to be strongly lensed, producing multiple images. There are, of course, various challenges of one is, for example, can we confidently detect strongly lensed gravitational waves? There have been some discussions on that. So this is work by, again, Ankur. It shows that with some, for example, at the current sensitivity, we will be able to detect if there was a lensed gravitational wave in the data, which we have currently ordered a couple of hundred events. You have about tens of thousands of pairs. And if you compare the accidental detection probability versus true detection probability, the conclusion is that if there was a lensed event in the LIGO data, we will be able to detect more than 60% of these events with a significance of 3 sigma or more. This is what is called an ROC plot, a receiver operating characteristic plot. It shows how the detection efficiency of an lensing detection pipeline as a function of the significance that we could claim in terms of false alarms, taking into account the fact that you have a trials factor, et cetera, et cetera. So this is, this is a 60% I talked about. But if you can, Ankur is currently working to extrapolate this to probe smaller and smaller false alarm probabilities, et cetera. And this is likely to be a lower limit because this is computing using a particular approximation of the likelihood ratio, which one could improve using some exact or a more accurate numerical calculations done by a joint parameter estimation, like Justin are working on. So there is okay, now you can also ask, what is the likelihood of seeing a lensed event? In the current data, it is not very large, maybe like 10%. There's about 10% probability of seeing a lensed event in the current data by folding in the optical depth, etc. Now, the problem is that in the future, when you have a large number of events, you have to check each pair of these events to check whether these are lensed or not. So your background would scale as n squared, while the foreground, the truly lensed events, would only scale as the number of events. Your optical depth is fixed. So there is a problem of lensing versus LEC. So this is a problem that is not yet solved, but there are possible ways of solving it, one would hope, because with future detectors, you'll be able to localize the sources, a large number of sources, much better precision. So we'll be able to improve the distinguishability better than what we have right now. Also with better parameter estimates, and perhaps also folding in the time delay information more cleverly, the possibility of type 2 images, microlensing signatures, etc. We had a discussion yesterday, and Srishti convinced me that, yeah, in fact, if you detect microlens events, that would actually significantly reduce the probability of false alarms, etc. So there are ways of addressing this, but it's not a solved problem. Assuming that it is solved, at some point in the next 15 years or so, one could ask, can we use the sample of a large number of lensed events that we will detect to do cosmology? So the typical numbers that one would require that you have 10 years of data from these 3G detectors, you will have about 10 million events, and even with a modest optical depth, something like a 10,000 would be strongly lensed. You would see multiple images from these 10,000 sources. And the precise number of strongly lensed events, as well as the distribution of their lensing time delays, would contain imprints of cosmological parameters, as well as the nature of dark matter. This is something I would show. Basically, it will provide us a new way of doing cosmography in the intermediate redshift range between the CMB and supernovae, as well as, in fact, slightly higher than the standard compact, the standard silent cosmology that gravitational waves promise to do. That's the idea. How do you estimate these things, the expected precision? So basically, you can look at how the expected number of lensed events would depend on the cosmological parameters. So one can do a simple calculation. Basically, one has to do a convolution. You take, there is some rate of mergers that we can have measured at low redshifts. The R is the rate of mergers. We do not have a good understanding of how these mergers are distributed at higher redshifts. So one has to currently use some models, that is this PB, binary merger redshift distribution, which is a function of cosmological parameters. And you have to convolve this with the corresponding strong lensing probability at that redshift. So basically, you have to integrate this over the entire redshift, so to Z max. Currently, we do not have an good understanding of how the binary black holes are distributed at high redshifts, so we have to use some models. But the good thing is that your data will be always dominated by the large number of unlensed events. So we will be able to measure these actual redshift distribution precisely with future observations. So it's not an unknown parameter in our calculation. Then there is some detection selection effect one has to account for. It primarily depends on the fact that you're only observing for a finite amount of years, and any time delay greater than that cannot be measured. So one has to factor in that. This one is a bit trickier. What is the lensing optical depth? One has to currently assume either currently what we do is use some halo mass function models and assume some simplistic lens models like SIS to compute the lensing optical depth as a function of the cosmological redshift and cosmological parameters. And this has to be improved in the future. Similarly, one can also compute the distribution of lensing time delays. So again, you have to, the time delay given a set of source parameters and lens parameters can be computed by solving the lens equation. So the distribution of time delay depends on the distribution of these sort of astrophysical parameters, like the source location in the lens plane, the properties of the lens. Here is the lenses are assumed to be a singular isothermal sphere, so there is only one velocity dispersion as a parameter. The redshift of the lens and the redshift of the source. These are the sort of nuisance parameters that we have to kind of integrate out. And the cosmological parameters. So, and if you have some distribution of these astrophysical parameters, the lambda, as a function of given these cosmological parameters, we can basically marginalize this over these nuisance parameters, the lambda, to get the expected distribution of the lensing time delay given a set of cosmological parameters. So it's sort of easy to see why these lensing time delay distribution would affect the cosmological, would depend on the cosmological parameters. There are at least, well, there are two effects. One is that the cosmological parameters would change the large-scale geometry of the universe. Basically, so you can see it from this is the time delay from an SIS lens model. So your redshift comes here, lens redshift, as well as the distance measure, the angular diameter distances. And the fact that the redshift and the angular diameter distances are related by cosmological parameters, similar to the Hubble diagram. That's why the lensing time delay has to depend on cosmological parameters. So if you are able to now, if you have a good model of these astrophysical distribution of these cosmological parameters and a good lens model, one could marginalize over these astrophysical parameters to get the predicted distribution of the lensing time delay as a function of cosmological parameters. This shows how the expected number of lensed events in about 10 years of observing time would change as a function of the, assuming a flat lambda CDM model, a function of omega m and the Hubble constant. So for large values, omega m and Hubble constant, you get larger number of events, and smaller values get a smaller number of events. And this shows how the time delay distribution as a function of time delay in log would change when you change the cosmological parameters. These solid lines, the dashed line shows the actual distribution of the lensing time delay, and the solid line shows how what you would observe given you have a finite observing time by factoring in the selection effects. You have a question? So this shows basically that we are trying to now given you have an observed number of lensed events and you have measured their time delay, the idea is that you can compute the likelihood for these cosmological parameters and write a posterior by doing a Bayesian parameter estimation. And this shows, for example, it's a forecast of the kind of constraint that one will be able to obtain, assuming fairly simplistic assumptions, using about 10 years observing time. This is a posterior purely obtained from this number of, this is the lensing time delay, and this is the posterior obtained from the number of lensed events, and they are uncorrelated. And so then the intersection has to be the right combined posterior. And this, again, the orange, these ellipses shows the combined posterior expected from about 10 years of its lensing observations. And in comparison, the blue shows the current constraints from Planck. So it's comparable, it would be comparable, so it's not very groundbreaking. But really, I think the real value is that it is probing a different redshift regime, sort of intermediate between the CMB and the supernovae. And okay, if you want to get, again, a sense of, again, the gravitational wave standard sirens, the binary black holes, which are our standard sirens, again, also promise to make a more direct measurement of these cosmological parameters by mapping basically the Hubble diagram. And this is showing an estimate of these sort of forecast of what you would get from the standard dark sirens plus the so-called spectral sirens, which Jose and colleagues have pioneered. Just the idea is to look for specific features in the binary black hole power spectrum. And essentially, you can see that these constraints from about are comparable to what you expect from these lensing also. So it's sort of one more, an additional information that you have for free from these gravitational observations. And it would have a precision that is comparable to the standard siren cosmology. This is sort of some ongoing work, which one of my colleagues, Kaustav Maiti, is exploring to see in the next decade, even before these XG detectors with the upgrades of advanced LIGO and so on, what kind of modest, can you get any modest constraints on these cosmological parameters? And the answer is you can get some modest constraints. They're not, again, groundbreaking, but maybe in the next decade or so, we will be able to get some constraints from if you have dozens of lensed events in the data. Let me also now switch gears a little bit to show how the lensing observation could also potentially probe the nature of dark matter also. And as you know, the standard model is the cold dark matter, which has certain amount of potential issues. One is that we have not seen any cold dark matter particles yet. So particle physicists have come up with various alternative models, and the simplest extension of this is called the warm dark matter, which basically attributes the dark matter to some thermal velocity. So it's not highly relativistic like neutrinos, but somewhere in between the cold dark matter and these neutrinos. So what would happen is that such free streaming of such warm dark matter particles would suppress the formation of small mass dark matter halos. It would suppress the halos at small scales. So this is sort of showing how the halo mass function, which is basically the number distribution of dark matter halos at various masses, would change when you basically give a thermal velocity to the dark matter particles. These are more relativistic. So you see that these are, as compared to the cold dark matter, which is the blue one, these sort of powers are suppressed at small scales without affecting the large scale halo mass function, which is sort of measured. So the idea is to suppress the poorly probed small mass scale without changing the well-measured large mass scale. So it would also then change the distribution of lenses in the universe, and in particular, it will change the distribution of lensing time delays at, in particular, small time delay values. So this is, for example, this is the same sort of a time delay distribution for the cold dark matter model is the gray one, and if you kind of go to these smaller masses of the warm dark matter, it particularly suppresses the lensing time delay at small values. Again, this is a feature that one could probe, And using a Bayesian parameter estimation, one could put upper limits on the lower limits on the mass of this dark matter particle. In our case, we choose to do it at the upper limit on the inverse of mass because of some data analysis reasons. This is sort of how this kind of constraints would improve as a function of observing time. To give you a reference, the current constraints, the observation of Lyman forest, etc., are much worse, like several orders of like maybe a factor of 10 worse than the current, what is possible using these future observations. So there are various challenges. One is we have to accurately identify lensed events, or at least to model our contamination fraction. If we're able to model our contamination properly, then there are possibilities of modeling it also and marginalizing it over. There are also uncertainties in measuring our source population distribution, but these uncertainties are likely to be negligible in the case of next generation detectors because of the large number of observed events. The hardest problem is going to be good modeling of the lens population in terms of the distribution of their properties, as well as good lens models. And this requires input from cosmological simulations, as well as a number of electromagnetic observations. So it's sort of a work that we have started only recently, and there are a series of papers coming out to kind of address these issues at various levels of sort of, resolution in the next years. So let me summarize. The first observation of lensed gravitational waves should happen in the next few years. And most likely lenses are galaxies. And the next generation detectors will detect thousands of lensed events, possibly tens of thousands. And their precise number of lensed events, as well as their time-delay distribution, would contain imprints of cosmological parameters, as well as the nature of dark matter. So it would be a new probe of cosmology, in particular in this sort of intermediate redshift regime. Thank you.